Welcome back to Applications of Stoichiometry. In this lecture, we'll be looking at predicted and experimental yields. In your textbook, it's page 304 to 309. By the end of this lecture, you will be able to perform calculations to determine the predicted yield for a reaction and compare the predicted yield with the actual yield of an experiment. You'll also be able to identify the causes for discrepancy between the stoichiometric calculations and the experimental yield. So a couple definitions. The stoichiometry that we've been working on can be used to test the success of an experimental design. And what we can do is we can test or compare theoretical yield to actual yield. And the theoretical yield is the yield we would predict based on stoichiometry. So we'd have a chemical reaction, we'd say if we have this much reactants, this is the amount of product that should be formed. Then an experiment's done, a reaction takes place, and some of the product's formed. This is the experimental yield. It's a yield that actually is created when you do the experiment. When the two are compared, generally speaking, the experimental yield is going to be less than the theoretical yield. And here's a list of reasons why, and then we're going to go through and talk about them each individually. So there could be competing reactions, so the reaction that we want isn't the only reaction that's happening. Sometimes the reactions happen so slowly that we may not wait long enough. Product can be lost due to human error. Sometimes it can go into solution when we don't want it to, or we can lose some. So mechanical loss is losing some during the process of the experiment. The reactants may not be pure, so when we weigh a reactant, if there's impurities in there, we're going to be weighing things that aren't actually reacting. And some reactions don't go 100%. So some reactions, not all of the reactants end up becoming products, and those reactions are equilibrium reactions. So with competing reactions, sometimes two chemicals can react in two different ways. So an example would be when we burn carbon, there's two potential products. One is carbon dioxide and one is carbon monoxide. And so carbon will burn in the presence of oxygen, and most of it will produce carbon dioxide, but a small amount will form carbon monoxide instead. So some of that carbon is going to be lost. If we're looking for a yield of carbon dioxide, some of that carbon is going to be tied up in carbon monoxide, especially if things are burning slowly. The more slowly you burn carbon, the more carbon monoxide is formed. So the yield of carbon dioxide would be less than predicted. Sometimes reactions are just really slow, and if you aren't patient enough and don't wait long enough, then the products that you're collecting, it won't be all the products you could have gotten if you had waited a little bit longer. So sometimes reactions are just slower than what we think they're going to be. The most common error is the most common error is the human error factor. One is dissolution. So ionic compounds with low solubility, and so when we look at our solubility table, and if you were to look at it now, you'd see that there are three rows, and the top row is just the negative ions. The second row tells you what's really, really soluble. And then the third row says slightly soluble, and up until this point we've been saying slightly soluble or soluble less than 0.1 mole per liter means insoluble. And of course that's an oversimplification of the truth. So it turns out that those things are slightly soluble, not enough to make a difference in terms of understanding chemistry, but enough to make a difference in what we would expect in terms of the amount of product produced. So something like lead chloride, or lead 2 chloride, it's insoluble, so most of it, in a reaction as the one that's shown here, is going to end up becoming a solid, and we can collect that out. But a little bit is going to be left behind in our solution. So some of it we won't be able to collect because it did dissolve in water. When the precipitate's collected, so once we get this solid and it's suspended in a liquid, once we start trying to collect it, some of it's going to be left behind. It's going to be dissolved in the filtrate. Some of it's going to be redissolved when we rinse it. So what we do is after a reaction is done, that solid that we collect, we rinse it with water to get any impurities out of it. But in the process, we put some of it back into solution. It gets dissolved in that rinsing water that we're using. So we lose some because it's left behind, and we lose a little bit more when we clean it to make it pure. The other cause of human error is mechanical loss, which is a fancy word for spilling. Reactants get spilt, stuff gets stuck and remains on glassware and filter paper and on spatulas when we try and collect it. So anytime we transfer something, a little bit gets left behind. And often people spill, we're only human. And so anytime you spill a reactant or product, that's going to lessen your result. Another reason why our experimental result is less than our predicted result is the reactants that we're using aren't 100% pure. Even ones that are of chemical grades that you see in laboratories aren't 100% pure. They might be 99.999% pure, but that still leaves a little bit of impurity. So when we weigh it, some of the stuff we're weighing isn't actually reactant. It's an impurity inside the reactant, and so it's not going to produce the product we're looking for. Finally, not every reaction goes to completion. Sometimes reactions can go backwards, and at some point, the rate of reactants colliding to form products is going to be the same as the rate of products colliding to form reactants. And so some reactions, like the one here, you get to a point where even though you're trying to react all that ammonia with the acetic acid, it gets to a point where the reverse reaction is just as common. So not all of your reactants go to form products. So not all reactions are actually stoichiometric. And so our percent yield, or the amount of product produced, is going to be much less than what we would like, or what we would expect if it was a straight stoichiometric reaction. So to calculate percent yield, this tells us how much product we actually got compared to how much we wanted. It's a fairly simple formula. You take the amount you got and divide it by the amount you expected, or the experimental yield divided by the predicted yield times 100. And that tells you what percentage of product you got compared to what you expected. So we'll do a few examples. Here we have a 1.55 gram sample of lead 2 nitrate reacts with excess aqueous potassium iodide. 2.01 grams of precipitate is produced. The theoretical yield is 2.16. Calculate the percent yield. And so for percent yield, we need two things. We have a theoretical yield, and we'll go like this. The yield based on theory, this question tells us, is 2.16 grams. The yield that we got, or the experimental yield, is equal to 2.01 grams. And so for percent yield, we have both things we need. Percent yield is equal to experimental yield over theoretical yield times 100%. The experimental yield was 2.01 grams. The theoretical was 2.16 grams. And we're going to multiply that by 100%. So 2.01 divided by 2.16 times 100, and we get 93. And again, we're going to follow our same sig-dig rules. We have 3 sig-digs in our question, so we're going to have 93.1%. There we go. That's the percent yield. The percent yield calculation is a fairly simple and straightforward calculation. Most of the times, however, you won't be told how much product you actually got. You'll have to find out using stoichiometry. So here we have acetone can be acquired by the decomposition of calcium acetate according to the following reaction. And so they give us a reaction. We want to calculate the percent yield if 10.31 grams of acetone are collected when 32.50 grams of calcium acetate decompose. So we've been given the experimental yield as being 10.31 grams, but we don't know the theoretical yield. So we've got to find that out. And the theoretical yield would be, I just want to make sure I write down the right one, calcium acetate. Oh, sorry, we want acetone, and acetone would be this one. So we want the mass of this produced. And we can find that, the theoretical value, through stoichiometry. So I'm just going to rewrite my formula, just so or my chemical equation here, so I have room to write down the values that I need to do my math. And now I can start filling things in. CO, this should be a C, my bad, CH3, and it's a liquid. And so what we want to find is the mass of this. Since we're looking for the mass, we're going to need its molar mass. And we've been given the mass of calcium acetate as being 32.50 grams. So we're also going to need the molar mass of our calcium acetate. So the molar mass of our calcium acetate is 158.18 grams per mole. The molar mass of our acetone is 46.08. 46.08 grams per mole. And now we're just going to follow our gravimetric stoichiometry. We're going to find the number of moles of our calcium acetate, use our mole ratio to find the number of moles of acetone, and then find our theoretical yield. So the number of moles, so because we're doing just gravimetric, I'm going to need molar mass is equal to mass over moles, and after I'm going to use my percent yield formula. So I'll just write down that. Alright, so number of moles of Ca CH3COO2 is equal to mass over molar mass, which is going to be 32.50 grams divided by 158.18 grams per mole. So 32.5 divided by 158.18, and we get 0.205 moles. And we know that the number of moles of CH3, COCH3, is going to be equal to 0.205 moles times 1 over 1. So it's going to be the same. So 0.205 moles. Now we can use that to find the mass of acetone, CH3, COCH3, is equal to molar mass times our number of moles. Our molar mass is 46.08 grams per mole times our number of moles, 0.205 moles. So we take our answer times 46.08, 9.46. So 9.4, and that would be an 8, or a 7, sorry, 9.47 grams. This is our yield, and it's the theoretical, because that's what we calculated. We calculated this is how much we should get. So now we're going to find our percent yield. That's equal to experimental over predicted or theoretical times 100%. And we're going to end up with, whoops, the experimental was 10.31 grams over 9.47 grams times 100%. So 10.31 divided by 9.47 times 100%, and we get 108.8. So 4 sig digs, 108.9, 108.9%. And so our percent yield is actually higher than what we predicted. Now, this doesn't happen very often. A couple of the reasons why it could happen is if you have impure reactants, it's possible that those impurities react and form something new. It could be in this case that some of these, since we're producing a liquid here, it could be that some of our calcium carbonate that was produced actually is dissolved in the liquid. So calcium carbonate is a pretty insoluble substance, but a little bit of it could be dissolved in the acetone, and in that case our mass is actually going to go up. When we weigh that liquid, some of it is going to contain dissolved calcium carbonate. So there are reasons why your percent yield can be above what you would expect, but most of the time it's below. One more example here. So here we have aspirin can be produced by the reaction of salicylic acid with an acetic anhydride with a percent yield of 65%. Determine the mass of salicylic acid required to produce 3 grams of aspirin. So here we have the percent yield, and because for whatever reason this reaction only goes about 65%, so it could be that it's maybe a equilibrium reaction, in which case there's a bit of backflow. It could happen really slowly and we just don't have our wait long enough, or it could be that just after a certain length of time the reaction stops. So there's a bunch of reasons why, but for some reason the typical yield is only 65%. So we know we want to produce, or we want an experimental yield of 3.0 grams. They also told us the percent yield is 65%. So from these two pieces of information, we can find out the theoretical yield. Once we do, that's going to tell us this mass. This mass is our theoretical yield. Once we get that, we can go back and we can find the mass of our salicylic acid. So now we have a little bit of plan. So on this page, I'm going to erase that line because it's bothering me. Okay, so we're going to use our percent yield formula to find out what the mass of aspirin, what we should predict the mass of aspirin to be. So our percent yield is equal to our experimental yield over our theoretical yield times 100%. We know the percent, so there's a couple of ways we can do this. I'm going to move everything over now. Some people are going to like to plug the numbers in first. Either way, we're going to get the same thing. So I'm going to move stuff over now. We want to isolate our theoretical yield. So we want to get this by itself. In order to do that, I'm going to multiply both. I don't like denominators, so one way to get rid of them is to multiply everything by the denominator. And so we're going to get the theoretical yield on this side multiplied by the theoretical yield on this side. And on the right, they cancel. On the left, we get our theoretical yield times our percent yield is equal to our experimental yield times 100%. And now to get the theoretical yield by itself, I'll divide both sides by percent yield. And on the left, the percent yields cancel. And now here I have a formula to find my theoretical yield. So that's going to be equal to 3.0 grams times 100% divided by our percent yield is 65. So 300 divided by 65. And so our theoretical yield is going to be 4.62 grams. And I'm going to keep as many digits as possible in my calculator. I'm only going to need 2 sig digs, so I'm just going to write down 3 for now. So this is our theoretical yield. That goes there. And so I'm just going to move to the next slide to get some more room for my calculations. So we know the mass of this is 4.62 grams. And now we're going to find out the mass of salicylic acid. So we're just going to do another straight gravimetric stoic problem. Alright, so we're going to find the number of moles of aspirin. There's an I in aspirin, look at that. There we go. So the number of moles of aspirin is going to be mass over molar mass. Our mass is 4.62 grams divided by 182.19 grams per mole. So the number of moles is 0.0253. Now we can find the number of moles of salicylic acid, which is going to be 0.0253 moles, times, our mole ratio is 1/1, so the number of moles doesn't change. But we always write down that mole ratio so that we know we've used it. And now we can find the mass. So the mass of salicylic acid is going to be molar mass times moles. Our molar mass is 140.15 grams per mole. Times 0.0253 moles. So times 140.15, and we get 3.55 grams. And we're only allowed 2 sig digs, so it's actually 3.6 grams. So 3.6 grams of salicylic acid will produce, I can't remember how much we needed, so I'm going to go back and look. 3 grams of aspirin. So there are some examples for experimental yield. There are some practice problems on page 308, and I will talk to you shortly about titrations.